Hi, everybody joining us. We'll wait another minute until we start as the number of attendees continues to rise. Okay. Hi, everybody. Thanks for joining us today. And for the last sessions of this week on the Chandra Frontiers in Time Domain Science, we have two Synergy sessions today. The first is starting now at 9 a.m. and the next one will start at 11 a.m. Eastern Daylight Time here in the Eastern United States. Really happy to that you can join us today. So without further ado, let's jump right into our first speaker. Our first speaker is Lia Corrales, coming to us from the University of Michigan, and she will talk to us about dust scattering echoes through cosmic time.
Thank you. Okay. Excellent. Great. Thank you. I'm very happy to be here. Thank you for inviting me. I'll be talking about dust scattering echoes through cosmic time, starting with basically the science of dust scattering echoes, some of Chandra's biggest hits, and then what we can expect from the future. So we will hear a little bit about this later, but I'm just going to start with talking about how X-ray scattering produces these spectacular dust echoes that we can use to do tomography or high precision mapping of the ISM. So as a quick little crash course into dust scattering echoes in general, what happens is we have plenty of dust in the ISM, and when you happen to have a bright X-ray source that passes through, where that light passes through the ISM towards us, it will scatter off of dust grains in the interstellar medium. So if you have a dust grain size of, we call this radius A, when the X-ray light hits it, it scatters over pretty small angles, usually on the order of 10 arc minutes. And because that's such small angle scattering, for any X-ray telescope with sub-arc minute resolution, which is nearly all of our X-ray telescopes below 10 keV, you get this little scattering echo, or what we call a halo sometimes, depending on whether you see rings or not, and if it's variable. So this is one famous dust echo that came out of this soft gamma ray repeater. But you can think of it in this schematic. So the dust that we're scattering off of is dust that's really intermediate between the original source and us, the observer. So we're probing the interstellar medium and not dust that's intrinsic to the source. And in particular, because we're scattering the light, it goes through a longer distance than the light coming straight towards us. So if you have an object that happens to go into X-ray outburst, it will take time for us to see the actual scattering halo, or what we'll call it a scattering echo. So because an ellipse describes basically any point where the distance between two foci is the same, you can think of the scattering surface as an ellipse in space. And as time goes on, the position of this scattering ellipse just grows. And then if you imagine putting a slice like a cloud in the middle of this ellipse, you get actually a distinct ring. So that's why you see a ring in this image and not something smooth. It's because you had an outburst. It started propagating through the interstellar medium and scattering in this geometry and producing a ring. Here's another schematic that's really nicely done. So again, you can imagine if you have this ellipse, which is kind of described as the surface of these points over here, and you have dust material that's at different distances, you're actually going to see a different ring corresponding to each cloud. So those rings, when you see them, they're actually not, sometimes it's due to the light curve, and sometimes it's due to the fact that there's a separate cloud. And as time goes on, the ellipse grows bigger, and so the rings grow as well. And the way that those rings grow is very characteristic of the distance or the location of that particular dust cloud. So here's that image again of the soft gamma ray repeater. This was done with Swift. It should start moving. There we go. So you can see that as time goes on, you see one big ring in the center that expands and a few other diffuse rings further out that also expand. So this is what we call a dust echo, and it's great for determining either the position of the dust, if you know the location of the X-ray outburst and its light curve, or conversely, if you have another wavelength that you can compare it to and you know where the dust is, you can learn more about your X-ray source, such as the distance or the original light curve. So this brings me to Chandra's biggest dust scattering hits. I just want to show pretty images and things we can do with them. So one of my favorites is this multi-wavelength study of a dust scattering echo from Circinus X1. In this particular instance, Circinus X1 went into a huge outburst, and the original science observation that was taken with Chandra was not meant to look at dust echoes. It was to look for remnants of a supernova or some sort of nebular emission. And it died down, making this observation possible, but what wasn't realized was that we would have these spectacular dust echoes. So this was imaged instead. And it's really fantastic because you can see different rings. So again, these rings correspond to different dust clouds. The multicolor image is made so that, you know, the lower energy is red and the higher energy is blue. And so you also see these different colors caused by different dust clouds and also an enhancement. So Sebastian Heinz went and looked at CO maps that happened to be obtainable in this in the direction of this source, and you can actually map which individual cloud was responsible for the scattering. So you can see an enhancement in brightness right here. It corresponds to this cloud right here, and so that's this little region. And then the reason that we see this blue feature is because there's actually a cloud in the foreground that's closer to us that absorbed extra light. So it's actually absorbing the background dust echo. So this is shadowing. And because the ISM absorbs more red light than blue, we're missing the red light from here. So this is a particular exciting instance where you can really study these clouds in detail with both dust scattering and in the in the submillimeter. And in particular for this object, by pinning down where it is and where the dust is, we were able to back out the light curve of the source. Another famous one that occurred just 1 year later was the historic flare of V404 Cygni. And this is the Swift image because they put together a movie for a press release. But again, you can see these really spectacularly bright single narrow dust rings, each due to a different cloud, and they grow with time. Yeah, it's just gorgeous. One particular thing about this observation, because you're able to watch them grow with time, that's really the part of the calculation that allows you to do high precision tomography. So this is what that image looks like together. There was supplemental Chandra imaging data that came with this. And you can see, because we actually know the distance to V404 Cygni, because it happens to be very nearby, 2.4 kiloparsecs, we know the distance because of radio interferometric measurements. And so in this particular case, we know the distance, so then we can back out where the dust scattering is, or where the dust scatterers are. So this plot here shows the abundance, the ISM column you would expect as a function of position along the line of sight. And you can see that the dust echoes give you quite high precision, and it agrees relatively well with measurements that were done with the Pan-STARRS EV-V 3D mapping. So what they did there is they look at populations of stars and how they appear to redden over distance, and that's what gives you a sense of the ISM column in that direction. but it's much more crude than what we can do in terms of spatial resolution with spectacular dust echoes such as these ones. And then my personal favorite, it's not a dust echo ring, but it was an X-ray scattering cloud that was confirmed to be X-ray scattering due to its light curve. So this is a modified image of Cygnus X3. And what I've done is I've just removed the median brightness as a function of radius, and it brings out in contrast this X-ray feature over here about 10, 15 arc seconds from the central source. In 2013, Mike McCullough did a paper on this source where he examined the light curve of SIG-X3. So this is the SIG-X3 orbital phase. And here you can see the actual light curve of SIG-X3. And then when you look at the light curve of this little object, you can see that it's actually shifted. It's about the same, but it's shifted in phase. And that is very good evidence that it's dust scattering because it's just a time delay from the original light curve of the X-ray source. And you can actually measure a distance to it given this time shift. And it's about 1 kiloparsecs away from SIG-X3 or 6 or 7 kiloparsecs from us. Later on, we did a follow-up measurement with SMA to try to figure out, can we confirm that this is actually a dust scattering cloud? Can we learn more about the properties of the cloud? And we were able to detect it in CO. So the magenta here is actually the blob that corresponds to the little friend cloud. And we have also shifted CO emission, which could be indicative of outflows. So perhaps there's a star forming in this cloud. So that was pretty exciting. And by getting a CO measurement, we're able to work on some of the degeneracies that we get when looking at radio observations of the ISM and start to look at what the actual distance to SIG-X3 was. So this is also one of my favorites. Okay, I'm going to move forward into some next generation science and where we can expect to go with dust scattering echoes in the future. So a few years ago, Sebastian and I started working on trying to figure out how many more spectacular dust echoes like we saw with Circinus X1 or V404 in the future, how many we can expect. And we went to the MAXI All Sky survey. So this is 9 months of the X-ray sky, but we were using the entire data set, which was about 10 years. And this telescope, which is operated by JAXA, just monitors all of the bright X-ray sources and publishes their light curves. So we went through and did a very simple search algorithm for figuring out when an object flares and when it's in quiescence. And there's a few ingredients that you need to get a good spectacular dust ring echo. So here are 2 examples of dust ring echoes that have been found. This is the flare that caused Circinus X1, the Circinus X1 echo. And this is another one around 4U 1630 that caused a nice ring. So the key ingredient is that you need a pretty big flare with a particular fluence and a high enough ISM column. And you also need the object to be quiescent for a long time around that flare, because if you have an object that just flares continuously or is often very variable, all of those dust rings just kind of smear together into a messy hodgepodge of a diffuse halo. So this is not really a good ring echo candidate, although, you could get lucky with timing in some sense, but for the most part, it's not going to be as spectacular and high contrast as we see with these types of flares. So in order to quantify that, I just literally take the flare duration and then I divide it by the quiescent duration for the light curve, either before or after the flare. So this ratio is plotted here on the x-axis. And then on the y-axis, you take the fluence of any particular flare and you fold through what the ISM column is in order to estimate what the total fluence of the dust scattering echo will be. And so again, here is every flare that we detected from the MAXI light curve catalog. Here's LNC-X3 type flares, so pretty low fluence, similar levels of flare duration to quiescence. And up here are the flares that cause the historic echoes. and some other echoes as well. So, and there's plenty that we missed. So I do a cut in parameter space in order to find anything where the flare is shorter than the quiescent duration and then above a certain fluence based on the background and sensitivity properties of Chandra, for instance. So these flares fit in there. So taking this population of flares from MAXI, we can plot a number density function as a function of fluence. And here I've selected echoes that are more, this is the flares, and then these are the echoes that they would produce. So we fit this with the power law. And then we go and say, all right, now that we know, now that we can extrapolate to lower fluence, what will we be able to see in the future? So extrapolating that power law, we're able to plot how different telescopes, well, how many more echoes they'll see relative to Chandra. So on the x-axis, we have the effective area of Chandra, and on the y-axis, we have the background rate of Chandra. So it's always a trade-off between sensitivity and background. So I'm on the CRISM science team, and we'll be launching with microcalorimeter instruments. We're really excited. And it's interesting to think about the fact that we might be able to observe some cool dust echoes and get spectra from them. And so depending on which instrument you're looking at, this is the microcalorimeter instrument and this is the CCD instrument, we could get on the order of 3 to 5 times more echoes than we can see with Chandra, just based on the background rate. Of course, when we have Athena or Lynx, we're expecting almost 100 times the effective area of Chandra. And even if we have the same background weight, we can really expect a lot more, about 30 times more. And so for these spectacular echoes, it looks like we're expecting one every few years. You know, up here, we're going to be getting like 10 a year. So this is pretty exciting. It also tells us that as people are looking at X-ray binaries, especially in the galactic plane, these dust echoes are going to become pretty ubiquitous, a pretty ubiquitous feature of what we see as we do other science with X-rays. I also want to talk about a subject that started me off in the field of dust scattering, and then I put it aside, and then I kind of came back to it after thinking more about the future of X-ray astronomy. So the initial question is, can we detect intergalactic dust pollution with dust scattering in the X-ray? And it really depends on a lot of factors, but in this particular schematic, I show the plots from a simulation of dust pollution and metal pollution from galaxies. And here you have windy galaxies filling a cosmological volume versus galaxies with no wind. And so the colors just show the abundance of dust and that's polluting the circumgalactic and intergalactic medium. And so you can imagine if you have a bunch of background quasars or AGN, the number of dust echoes, where I've put in these dots to represent potential populations of dust echoes, the number that you see in the sky will just tell you, one, how much pollution there is, so the filling factor of the intergalactic medium. But you know, it can also tell you how efficiently galaxies are able to pollute. So looking at this, I said, okay, what is going to be the typical brightness for these dust scattering halos? And it turns out, depending on whether you're looking at diffusely distributed dust everywhere or a particular foreground galaxy, it's incredibly dim. It's on the order of a few percent of the point source light going into the scattering halo. And of course, even with the exquisite resolution of Chandra, that's still way lower than the PSF and the background. So for a while, I gave up and said, we're never going to see this. But later on, I realized, you know, what if you have an AGN that was bright 100 years ago and it turned off? And we do have some sense that AGN accretion should be stochastic. So here's just an example of a simulation where they're feeding an AGN. And this is the fraction of Eddington at which the AGN is accreting, and you can see that it changes and all of a sudden can like change and switch off very quickly. So if you imagine that you have an AGN at different times in their life cycle, whether or not you catch them in a low phase versus a high phase will tell us whether or not we can see the dust scattering halo or the echo from their previously active phase. So you imagine catching some AGN in this phase right at the bottom of a big outburst, and all of a sudden the PSF is lower, but the dust scattering echo is still there. So in this case, the number of dust scattering halos that we see from, out around AGN or in the diffuse intergalactic medium depends on the filling factor, as well as the life cycle or duty cycle for AGN accretion. So doing a very quick order of magnitude estimate, you can get the number of echoes that you expect in the entire sky, taking the time delay for the dust echo, which can be between 1 and 1,000 years, depending on the population of the dust and the redshift. The frequency for AGN disruption or just turning off due to some sort of instability. So looking at the literature, I came up with an estimate of once per 10 to the 3 or 10 to the 6 years. And then the final value is the number of AGN above a certain threshold flux. So one, you need AGN that are pretty far away so that you have a large enough ISM column, but also you need the flux to be large enough when they are active that you actually produce a dust scattering halo or echo that's above a background rate. So for instance, for Chandra. And when I originally did this work, I looked at Chandra in particular, and I realized, well, we would only get one echo in the sky. So that's basically negligible, so I put it down. But later on, people get really excited about this particular subject. People were coming to me and said, but we should be doing so much better with our next telescopes because they're like 100 times more sensitive almost. So I've redone this calculation for things that are on the order of 50 to 80 times the effective area of Chandra, and it looks like those number of echoes can be more like 10 or 30. So that's still very few around the entire sky, but it's an exciting prospect because you might serendipitously just discover a ring out of nowhere with no source in the center at high galactic latitude, and that could be indicative of one of these dust scattering echoes. I should also point out that resolution has a big feature in identifying these things because these dust scattering echoes can be quite compact. So you're not going to notice that it's a ring unless you have high enough resolution to resolve the fact that the center is hollowed out. So something like Chandra or Lynx is really much more ideal, especially because, again, as you get further away, the dust that you're scattering through is just going to make it more compact. But it's pretty exciting to think about. Okay, and then finally, the other thing I'm very excited about is looking at these dust scattering echoes and dust scattering halos in general to do astromineralogy in individual clouds. So if you imagine you have a high resolution X-ray microcalorimeter type instrument where you can get a high resolution spectrum out of a spatial image, you can obtain a spectrum of the dust scattering halo. And when you normalize it by the point source spectrum, you should get features that look like this. So this is the scattering opacity of the interstellar medium for two different types of dust grains as a function of energy. And when you have absorption resonances, you also have scattering resonances, and you produce this X-ray scattering fine structure. And this is kind of showed in lower resolution, but essentially you get these big dips in the scattering cross section. And this is your direct proof of particular elements being uptaken into solids. And if you have a high resolution spectrum of these features, you can also identify the minerals that are producing the scattering. So that's something I'm particularly excited about. It's something that we want to do with CRISM. Here's an example of a measurement that was done like that for SIGX2 with CCD X-ray imaging spectroscopy, which is 100 to 200 EV resolution. but is something that we're going to do much better with XRISM, Athena, LINX, etc. So this is, for instance, a simulation of a XRISM spectrum around the oxygen features for GX339-4. And if you take a point source observation in green versus a halo observation in purple here, and you normalize the two, or normalize one by the other, you get out the scattering features, for example, from solid oxygen species. And I'm happy to announce that the lab cross sections for some oxygen species have recently become available from Iona Sararaki, who's working with Elisa Costantini in the ESROM group, working on these cross sections. And she'll be joining my research group in the fall. I'm sorry, in the spring.
3 minutes.
Thanks. And so I find this really exciting, especially in the era of Athena and LINX, because XRISM is particularly low resolution. So we will be looking for these types of features from dust scattering halos. But you can imagine in the future when we have another one of these spectacular dust scattering echoes where we can start to really discern different features from different individual clouds. You can imagine taking a detector, your X-ray microcalorimeter, and saying, okay, I'm going to get a spectrum of the point source here, and I'm going to pick out this region right here, and I want to see what minerals are in that cloud. And so this is an example of what you can do. So for instance, you divide one of the spectrum by the other, the point source divided by the halo in this case, and you'll see different features based on the crystallinity, for instance. This is amorphous pyroxene versus crystalline olivine silicates, and you'll be able to do that mineralogy right away. So this is what I'm excited about in terms of the future of both X-ray tomography and also just mineralogy of dust in the interstellar medium. So I'll end here with my conclusions, and I'm happy to take questions. Thank you.
Thank you, Leah, for an excellent talk. Please enter your questions into the Q&A box down at the bottom of your Zoom window. We do have several questions, so I will read these questions to you. The first question is from Daryl Haggard, who asks, how sensitive are these measurements to the properties of the dust itself, composition, grain size, distribution, etc.?
So yeah, so dust grain size distribution is really important. Oh, I see. So I think I'm a little bit confused as to what Daryl means by these measurements. I'm going to suppose that you mean the tomography portion. So yeah, so the dust grain size distribution definitely is a source of degeneracy for some of these measurements. So for instance, with the dust scattering halo of Cygnus X3, I showed that you can put the dust scatterer at different positions based on whether you had big dust grains that were close to us, so close to the observer, versus regular small ISM dust grains that were further away from us and close to the point source. I would say when you have the time information, it really breaks a lot of those degeneracies. So when you're able to watch the dust echoes grow with time, it breaks a lot of that. In terms of composition, I would say that that affects mostly the brightness of the echoes. That's just my first intuition on that.
And you were correct, that was the tomography. The next question is from Pragati Pradhan. How challenging is it to disentangle the emission from dust versus other interstellar absorption, like clumps in the stellar wind of AGNs and X-ray binaries?
Awesome. Yeah, so in absorption spectroscopy, I would say that it is difficult sometimes, particularly difficult to disentangle the dust features that are intrinsic to the ISM versus intrinsic to the binary. For the most part, I don't know of AGN spectra where we see dust features. Normally we're looking at normally we're looking at sources that are galactic because they're bright enough for us to do high signal to noise stuff. But in general, most people assume that the X-ray binaries themselves are too high energy of an environment for the dust to really to survive. Now, that's not necessarily true because I'm on a paper where we look at the iron K emission lines and features, and there's evidence that there's actually fluorescence from dust in the vicinity of the X-ray binary. So it is an assumption that's worth challenging, but in general, that's what we assume. The other thing is usually with high resolution spectroscopy, we can at least discern some of the higher ionization species from the neutral or the solid phase species. So that's usually what's contaminating our spectra. But when it comes to the dust scattering echoes, that's another reason that I want to do high resolution spectroscopy with the scattering halos and the echoes, because you can kind of test some of those ambiguities and looking versus looking at just absorption.
Great. This one's from John Miller. Could X-ray bright TDEs produce dust rings, e.g. would Swift J1644 have produced rings?
That's a good question. I don't know a lot about that particular TDE. I would say, I mean, it just really comes down to measuring the fluence, and Sebastian and I are pretty good at monitoring ATELs, and when we see something with a reasonable fluence, we usually talk about it. So I feel like I want to pass that question to Sebastian. But yeah, anything that flares will produce a dust echo if there's enough dust in the line of sight.
Great. And one question from Jorge Quadra. Could this dust scattering technique be used to measure the 3D structure of the central molecular zone in the galactic center?
Yeah, that's a great question. So one of the things that I was really interested in for a while was looking at all of the compact objects that pop off in the galactic center region and the galactic bulge, and say, what can we do in terms of understanding the distribution of dust in that area? So in that particular case, one, you need bright enough stuff and high enough cadence observations to do it. I think that there is a lot of promise. The central molecular zone, that's a much broader feature, I think, than can really just be done with Chandra staring at the galactic center. I always confuse the terminology, but it's definitely something that's worth thinking about. And a bunch of us have kind of talked about it a little bit, but we haven't actually worked that hard on the project yet. But yeah, I will say at least I do want to add, so I do have a paper on dust scattering around a few compact objects in the galactic center region. And then there's also a really nice paper by Jin et al. Doing AXJ 1945. And he does a little bit more in terms of identifying several dust slabs versus one or two, at least towards the galactic center.
Here we have a question from Bree Mills. I think you saw it too. I saw it. It's pretty interesting. So would we be able to see extragalactic halos with next-gen telescopes?
Yeah, so the dust scattering echoes I was talking about around AGN, I consider all of that extragalactic because it's really scattering off of dust that's outside of our galaxy, at least. So we haven't quite seen that yet. We have seen dust echoes around gamma ray bursts, for instance, that echo off of material that's kind of, that's in our galaxy, like within our gravitational potential. But definitely for sure, one of the things I'm interested in is finding those dust scattering halos from perhaps the CGM of another galaxy, which I would consider extragalactic.
And in a similar vein, but more directed, it's another question from John Miller. Over the whole sky, are AGN dust rings a measurable fraction of the cosmic X-ray background?
That's a great question. There is a paper on that. It's Dijkstra et al. From like maybe like 2005 or something like that. And Hobby Loeb's on it too, I think. I'm not sure. But basically they look at, yeah, the number of AGN in the sky and then how much dust scattering you might expect given like a few cosmological guesses for the abundance of dust in the IGM. And it's actually pretty negligible. So I'm just gonna go with no.
And I want to ask a quick question on the Synergies topic. You use MAXI a lot, and MAXI is, I think, slated to run till 2021. Are you using MAXI to trigger these other observations, or is it just to find the potential sources? And what do you plan to do when MAXI is no longer available?
Yeah, that makes me sad. So we're not really using MAXI to trigger. Mainly we monitor ATELs. So the MAXI work was really to look at the past 10 years and to say, okay, which ones did we miss? How can we estimate what we're going to see in the future? But yeah, normally we rely on ATELs because those are the most, the highest fluence type of events.
Great. Thanks so much for an excellent talk, and thank you for the questions. Next speaker, can you please share your slides? Our next speaker is Mario Giuseppe Guarcello, who's going to talk to us
Close
about
enough.
going to talk to us about simultaneous optical and X-ray variability in young stellar objects from the CS12264 project. And Mario's coming to us from Palermo at INAF.
Okay. Oh, thank you very much. Thanks for giving me this opportunity. Do you hear me? And do you see the pointer moving?
Yes.
Okay, perfect. So what I want to do today is to show you the capability of the studies in the time domain, combining optical and X-ray data to study the properties of the young stellar objects. And what I want to do is to show you this by using the results taken in the framework of the CSI 2264 project, which was a project focused on the young cluster NGC 2264, which is less than 4 million years old. It's very rich of prime sequence stars. And I will focus on the results obtained from a Chandra observation, 300 kiloseconds long, divided in 4 different epochs, and taken simultaneously to the CLOUI observations. CLOUI was this wonderful satellite that was designed for the search of exoplanet and was performing optical light curves with a cadence of 50 and 300 seconds, so with a wonderful cadence. And in particular, we have 374 prime sequence stars in this cluster for which both X-ray and optical data are available. So first, why we're interested in this science? The prime sequence stars, mainly when they are very young, younger than 5 million of years, they are typically surrounded by a protoplanetary disk, which is a disk of dust and gas orbiting around the star, and that may evolve in a planetary system. Now, the very inner region of this disk are actually quite crucial for several reasons. For instance, for the magnetic coupling between the star and the disk, the accretion of gas from the disk onto the star, and also for the evolution, it plays an important role for the evolution of the angular momentum of the entire system. The problem is that this region is very narrow. I'm talking about a few 0.1 astronomical units. For instance, if you take a look at this image of a protoplanetary disk around the star HL Tau taken by ALMA, the extent of this disk is about, the radius is about 200 astronomical units. So this region is a very narrow spot inside the disk. So it's very difficult to actually directly study and probe this region. I want to show you that with studies in the time domain, we can actually do it. So first, prime sequence stars are variable sources. And this was one of the properties of the prime sequence stars considered by Joe in 1945 to define this new class of object called the T Tauri stars, which are prime sequence stars with disk. I mean, it is evident if you just look at this optical light curve, these are very old light curves of 2 T Tauri stars. And for instance, you see there is a variability of almost 2 magnitudes here. Now, this variability is due to several phenomena. Among these phenomena, the 3 main phenomena I'm going to show you now. The first one is rotation and magnetic activity. This, of course, is not a prime sequence star. This is the sun, quite old. And these are images taken by the SDO. Now, if you take a look at the photosphere, during the rotation of the sun, you see the appearance of a magnetic active region in the photosphere, which contains spot. Simultaneously at the same location but at different age, you see the corona. There is the appearance of a X-ray bright active region in the corona. So if we were looking not at the sun, but if we were looking at to a distant star, so we are not able to resolve the details of the star, we could see a decline of the optical emission because of the appearance of the spot, and an increase of the X-ray emission because of the appearance of the active region in the corona. So these magnetic activities can affect the variability of the stars, and the prime sequence stars are very active from the magnetic point of view, thousands of times more active than the sun. The second phenomenon is variable extinction. In this case, for instance, in this case, we have a disk rotating around a star, and the inner disk is not flat. It has structures, these homogeneities, that can obscure the star during the rotation of the system. Of course, when one of these structures come in front of us along the line of sight, we have an increase of the optical extinction and an increase of the X-ray absorption that, as I will show you, can help us probing the properties of the material. And we also have accretion, as I said before, accretion of gas from the disk onto the star. This accretion can be completely unsteady, like the accretion shown in these simulations made by Colombo and collaborators. This is the disk, this is the star, and these are accretion funnels of gas that turn on and turn off after a while. So the emission of this process, which is an emission in optical, mainly in the most energetic part of the optical band, UV and soft X-rays, is intrinsical variable and can also be modulated by the rotation of the star. So again, this is an intrinsical variable and multi-wavelength phenomenon. So now let me show you what we have done to 2264. We've been able to use the optical light curves of the stars in this cluster to actually isolate those time intervals in which there was something important going on. For instance, take a look. This is a nice light curve in black taken by Corot of one of the stars in 2264. This light curve is not flat, it's not sinusoidal, is a mess dominated by spikes, which are accretion bursts, like for instance this one, or dips, like this one, which are due to an increase of the optical extinction. So we define the time intervals isolating this phenomena. We extracted the X-ray photons during these time intervals, and we performed what we call a time-resolved X-ray spectra analysis, fitting the X-ray spectra to 1 temperature, 2 temperature thermal plasma models, all in those time intervals. So now let me show you the results, some of the results. For instance, let's consider a star with optical dips. So this is the light curve of one of the stars in 2264 with the optical dip. There is a large dip here and 3 narrow dips, which are due to an increase of the optical extinction due to the circumstellar material. We have done this calculation, and in this case, we were looking for variations of the X-ray absorption, the NH, which is 0 during all the time intervals with 2 exceptions. And in particular, in both cases, we have in these 2 intervals 2 optical dips. And in this case, as you can see here, the increase of the NH is also significant. So we have here a very nice evidence for a simultaneous increase of the optical extinction and the X-ray absorption, and also an evidence for the capability of the circumstellar material actually absorbing the X-ray photons, which is something useful for several theories, like for instance the photoevaporation of the disks. But we can do even more because, for instance, in 6 dips, we've been able to calculate some of the quantities of the dips. NH, AV, the full width of maximum, the rotation period of the star. And so we calculated some of these ratios. For instance, you can see the plots here, NH over AV and the ratio between the full width of maximum, the rotation period of the stars. And the values that we found using the results taken by the project are typical of intervening material, which is gas-rich and confined in very narrow structures. So something you expect from accretion streams, which are likely due the cause of this simultaneous increase of optical extinction and X-ray absorption. So talking about accretion, this is one of the light curves of one of the stars in which is dominated by accretion bursts. You see that all these spikes in the light curve. There's a very big accretion burst here. We repeated the calculation. This time we fitted the X-ray spectra with thermal plasma models, and there is no way to fit during this burst, for instance, to fit the X-ray spectrum with a 1 temperature model, thermal plasma model. You need 2 temperatures because of this excess of soft X-ray emission here. So we have some evidence for the fact that during the optical burst, we can detect the soft X-ray emission, which is quite important because, as I said before, the soft X-ray emission is connected to the accretion process, but has always been very difficult to actually distinguish, to actually resolve this soft X-ray emission because people didn't have these light curves to isolate the burst, and it was difficult to distinguish it from the coronal emission from the star. And it can be useful to probe the accretion process. We can do even more. We have taken all the time intervals we have defined, and these time intervals we have fitted the X-ray spectra with a two-temperature thermal plasma model. We have calculated the ratio of between the normalizations of the soft and the hard component, and you see that there is a bunch of time intervals in which there is an evidence of a significant soft X-ray emission. And most of these time intervals, the black dots, are actually time intervals in which we observed the optical burst. So again, we have with this very good evidence for this presence of soft X-ray emission during accretion that, as I said before, can be used as a diagnostic for the properties of the accretion process. So in the last minutes, let me show you what we have done for the stars without disk. We have repeated the approach, but this time what we have done was to sample the optical flux and the X-ray flux. So the optical, in this case, we have a light curve. This is the optical flux. This is the X-ray flux. In order to search for the correlation between the optical and the X-ray variability. And in this way, we sorted the stars without disk in three groups: those with correlated variability, anti-correlated, and non-correlated. These are a few examples. For instance, in each of these plots, you have the X-ray flux and the optical flux. In this case, there is anti-correlation. In this case, there is correlation. That I'm going to go a bit fast here. Now, the anti-correlated variability can be understood if we remember the rotating sun as the simultaneous appearance along the line of sight of dark spot in the photosphere causing a decline of the optical light curve, and bright spot in the corona causing an increase of the X-ray emission.
Minutes.
Thank you. By the way, we also can connect this variability with the properties of the stars. For instance, the rotation of the star. This is a plot in which you see the rotation period of the stars and the three correlation classes: anti-correlated, non-correlated, and correlated. And there is a clear difference. If you see here, for instance, all the anti-correlated sources but one rotate slower than the correlated sources but one. This is a very nice evidence for the fact that rotation plays an important role on the correlated variability between optical and X-rays. We played a bit with the literature. We have used the results by other people to actually build a scenario in which the stars which rotate slower, the primitive stars which rotate slower, typically have a more ordered magnetic field. And this results in a population of a small number of spots, but larger. So something that you expect from spot-dominated sources. So in this speculation, because this is a speculation, anti-correlated sources are spot-dominated sources. Of course, there are projects like, for instance, MATIS, in which the correlation between the topology of the magnetic field and the properties of the stars will be studied in great details. In this picture, then, it's obvious that the faculae dominated sources are likely, the correlated sources are likely faculae dominated. In this case, the effect of the dimming of the optical emission due to the presence of the spot is overwhelmed by the presence of the network of faculae, which cause an increase of the optical emission. Something that we know actually occurs in the sun when the sun is in this maximum of its activity cycle. And the network of faculae cause an increase of the total irradiance of the sun. So I ran out of time. So I just want to leave you with the conclusion. I hope that I convince you that studies in the time domain combining, so in the multi-wavelength regime, combining optical, X-ray, and other wavelength is very powerful to probe properties of the young stellar objects that otherwise are quite difficult to study.
Thank you, Mario, for an excellent talk. Please enter your questions into the Q&A box. We have a question from Rafael Martinez Galarza. When a pre-main sequence star flares in X-rays due to a magnetic event, what is the range of X-ray variability that you expect? By how much does the Chandra broadband flux typically increase? And what is the maximum variability measured so far?
That's a tough question. No, we have, there is a nice paper on this project that has studied flares in this project, so in the stars in 2264, and there is a wide range of possibilities. So you go from very narrow flares to super flares, in which there is an increase by order of magnitudes of both the optical and the X-ray variability. So there is a very huge range in which these quantities vary. But it is also nice here to perform these studies in the multi-wavelength regime, because in this way you can probe both the properties of the hot plasma filling the coronal loop and the material in the photosphere which is heated by the whole flaring process. So in this way, by combining optical and X-rays, you are probing both what is going on in the upper atmosphere in the corona of the sun and what is going on in the photosphere. So it's an excellent tool actually to probe all the interplay between different phenomena during flares. It's something that we have done, for instance, in the Pleiades, and is another excellent field for the a multi-wavelength approach in X-rays and optical and infrared and so on.
Great, thank you, Mario. I think that's all the time we have for questions. Will the next speaker please prepare their slides? Okay, our next speaker is George Chartas, coming to us from College of Charleston, and will talk to us about microlensing a quasar's accretion disk.
Okay, everyone. Good morning, and thank you for inviting me to this meeting. So for today, I would like to focus on microlensing and how we can use this technique to constrain some important fundamental properties of quasars. So I'm going to start off with just describing the basic environment of supermassive black holes, and describe how we can use microlensing to constrain the sizes of the corona, the accretion disk, the spin parameter, which is a very difficult parameter to measure. There have been many attempts, and I'll present one particular method here. And then I'll end with talking about future projects, prospects, and how upcoming missions can be used to study these quasars even in more detail. All right, so let me start with what we think is going on today. So we have this accretion disk around a supermassive black hole. We have this hot corona, and photons, optical and UV photons from the disk, we think, are upscattered to X-rays. So we have this direct line here of X-rays coming from the corona. Some of these X-rays will get reflected back on the disk. The ones that reflect off very close to the black hole will experience GR effects and special relativistic effects, where the ones that are scattered and reflected further out will not exhibit those effects that strongly. So what's important is like the reflected spectrum actually contains these very strong fluorescent lines that are used as diagnostics to study gravity very close to the event horizon. So one of the key lines that's used a lot in studies of AGN is the iron line. And also you notice there are many other lines as well. So here in this spectrum, you see what the incident spectrum is from the corona. And then you can see on the bottom what the reflected spectrum looks like. And then further up at higher energies, we have what's called the Compton hump. Okay, so let me briefly describe what gravitational lensing is. So here you have this distant quasar, and there's a galaxy in between us and the quasar, and light from the quasar is actually bent along different paths, and there's a time delay with respect to different paths. And instead of seeing one quasar, you see multiple images of that quasar. And on the top right, you see 4 images in this example, and you see the bulge of the galaxy in the center that's causing the lensing. So Another way of representing this is in this diagram here. You see Chandra, obviously on the left, which is X-ray emission capable of resolving the images of these lens quasars. And in this case, what I want to show here is first you have the deflection of light due to the total potential of the galaxy. All right, but then you have stars in the galaxy that individually cause an additional bending of light. That's called microlensing, because those deflections of the order of micro arc seconds. So we can actually see those deflections. But what they do is they produce this network of caustic magnification patterns on the disk. So you can imagine you have this accretion disk, and this magnification pattern is just crossing the disk. All right, and magnifying small regions of the disk. Now, why that's important is typically when we take a spectrum of a quasar, we're averaging, integrating over the entire disk. So we're blurring all those reflection lines, right? Whereas when you're looking at a spectrum that's being microlensed, you're essentially magnifying a small region of the disk. So those lines are not blurred. And so you can actually hopefully see those lines and also study how GR affects the shape and energy of those lines. All right, so here on the left is a simulation of what these magnification caustics look like. And in the circles, I show two different sizes of a source. So you have a very big source and a very small one here. So I'm going to try to describe the essence of how you can use microlensing to constrain the size of a source. So just imagine this small diamond here, this magnification caustic, and it's going across and the big circle. It's only going to magnify a small portion of that big circle. So large sources will not experience a large enhancement in flux when a caustic goes through. Whereas just imagine now this diamond caustic going across that little source, it will magnify the entire source. So you will see a very large enhancement of the flux from a compact source. So that's the main idea. Small sources will be affected strongly by microlensing, and large sources will not experience it as much. And on the right, I'm showing you what a typical, how the magnification is close to a caustic. It's not symmetric. So if you approach a caustic fold, let's say from the outside, it's almost zero magnification. All of a sudden you hit the caustic and you get the strong magnification, and then it gradually decays. And there are two characteristic timescales: the time it takes to for the source to cross the fold, and the time it takes to go from one side of the diamond to the other, which is the essentially called the Einstein crossing time, which is much longer than the source crossing time. All right, so this idea of using microlensing was actually modeled more accurately back in 2004 by Chris Kochanek, who actually created a model where essentially you parameterize the source, let's say the optical and the X-ray source. You can create a distribution of stars with different masses in the galaxy. The model also includes a parameter for the fraction of dark matter to normal matter in the lens galaxy. So essentially what you do is you simulate these a network of magnification patterns, and you take your source and you move it across this network, and you produce a simulated light curve which you fit to your data. And you have a metric like a chi-square. You do that maybe millions of times until you get a good fit, and you do it simultaneously to the X-ray and optical data. So I'll show you how we implemented this technique to Chandra observations in the X-rays shown in the top, and then optical observation in the bottom. So what I'm plotting here is the flux ratios, because these are magnitudes. So essentially B minus C is a flux ratio of B of C over B. So essentially what you're seeing now is very large changes in the flux ratios in the X-rays. You see that very large magnitude changes, where the optical there aren't very, so going back to what I was saying before, compact sources, you expect to see very large changes in due to microlensing. Larger sources will see a less effect. One thing I want to point out is we know quasars and general AGN have intrinsic variability in addition to this microlensing variability. When you take the flux ratio, the intrinsic variability actually cancels out. So all you're looking at here, this variability is mostly due to microlensing. All right, so at the end of the day, once you finish this analysis, what you end up with is a distribution of sizes for your source. All right, so the X-ray source from this analysis, which is shown in the top panel, the distribution of sizes of the corona is about 10 Rg. This solid vertical line is 1 Rg. So you can see the X-ray corona is very compact, 10 to 20 Rg. And if you look in the bottom panel, what we show is the size of the optical emission disk at 2,500 angstroms, and it's about 100 Rg. This is work that was presented in a paper by Dai et al. In 2010. All right, so we actually performed such an analysis to many more quasars, and what I'm showing here is the size of the X-ray corona essentially as a function of black hole mass. And you see that, and this dashed line is essentially 6 gravitational radii, essentially the event horizon of a non-spinning black hole. But, so what you see is the sizes we get are very small. So this was kind of a nice result, implying that indeed the corona is not really extended over the entire disk. It's very compact. And this result is consistent actually with reverberation mapping methods where in the X-rays where they look for time delays and time lags. And Aaron Carr will give a talk on reverberation mapping in a few weeks in this meeting. So I suggest going to that talk to hear more about that. Also, from the same type of analysis now from microlensing, we can constrain the sizes of the optical emitting disk. This is at a radius of 2,500 angstroms. And what we see, like the data points here, are the results from the microlensing analysis. And the crosses are the results from taking the observed luminosity and plugging it into the standard thin disk theory. What we find is the observed microlensing sizes are a factor of 3 or 4 larger than what the thin disk theory predicts. So this caused a lot of discussion when we first presented. This was in a paper by Morgan et al. And there have been various attempts to explain this. Maybe a clumpy disk, maybe a disk where the temperature profile is more shallow than what we think it should be. But this result is also confirmed by reverberation mapping in the optical in different continuum bands. Again, this is an ongoing study of if this is real, and if it is, what's causing this. All right, so let me get back to this synergy of using X-ray telescopes and optical telescopes to constrain the properties of AGN. So we'll be monitoring these quasars here in the X-rays using Chandra. Chandra is the only current telescope that can resolve the images. And we'll be monitoring in the optical initially with the SMARTS consortium telescope, but more recently the Cosmograil team has been monitoring many lenses for getting time delays, which you probably have heard are very useful for constraining cosmological parameters. So we'll also be monitoring them to get UV light curves we'll be using the Hubble Space Telescope, and you see some beautiful images of these lenses taken by the Hubble Space Telescope. The one on the left is the object that I'll be mostly talking about today, quasar redshift of 0.658, and you see the 4 images and the galaxy in the center here, all right? And this now is a snapshot of Chandra observations of that RxJ 1131, and notice how the flux of the images changes with time, very noticeably. And some of that is due, again, to the intrinsic variability, but some is due to microlensing. All right, so this is now the whole data set. This is 15 years of monitoring RxD 1131, both with Chandra and in the optical band. So the blue points connected by the dashed line are the X-ray data points. So obviously they're not as many. You can see that the optical data points in the R band are, there's a higher cadence, and especially the Cosmo, as I mentioned, Grail team is using the optical light curves to constrain the time delays. So what you notice here, these are flux ratios. So as I said, if there's no microlensing, you should see a flat line. So if you look at the top panel, there are cases where you see these huge enhancements, more likely microlensing in image A in this case. And you see like in around 4,000 Julian date, where there are like two little peaks, and then around 5,000, two more peaks. So this is essentially the source crossing the caustic, the diamond, and every time it crosses a fold, you see that little separate peak. So essentially, this time scale here for one of these peaks is essentially the caustic crossing the corona. And you can easily use that to constrain, just by looking at this, the corona size. But you also can see that some cases you see microlensing events in the X-rays which are not detected in the optical at all. All right, so if we now look at the spectra of these images that during periods where there's microlensing, we find these lines, which we think are from the reflection component, as I showed before. And as I mentioned, the strongest one is iron. But the line, first of all, doesn't appear at the 6.4 keV energy. This is an observed frame. So redshifted, this is where the iron K alpha line should appear. So this is, we think, because the caustic is very close to the event horizon, so GR effects have redshifted the line. The reason why there are two components is because the caustic is magnifying emission coming towards us on one side of the disk and away from us on the other. And this is one image here, A, and we see in all images, but not always at the same time. So when this is happening in image C, the spectrum of the other images don't see anything. So this is another proof that this is indeed microlensing. All right, so what we did is we compiled the distribution of energy shifts, so of this iron line over the 15 years, and you can see there's they range from about 2 keV all the way up to 8. And again, 6.4 is where you expect the iron line to be if there are no shifts at all caused by GR or special relativity. So we use this distribution actually to constrain the innermost stable circular orbit of a black hole. Why? Because just imagine this boundary here, 2 keV, is when the caustic is at the closest it possibly can be to the event horizon. So we're detecting emission here, probably very close to the ISCO, the innermost stable circular orbit. So what we did then is we calculated what we expect that shift to be due to GR and special relativity. So essentially that ratio of the observed energy of the line to the emitted line is just a component that depends on the Doppler factor, how fast is the material going at a particular location, and a component that shows how much should the line shift because of general relativity, which incorporates the spin of the black hole. So we calculate G then as a function of radius, and I plot this now in the center panel here. You can see G as a function of radius. There are two bands here. The top corresponds to the part of the disk coming towards us, and the bottom from emission going away from us. All right, and on the left, again, I show that distribution of observed shifts that we've seen. And if you take these two boundaries, the radius that's consistent with those two boundaries of shifts is about 3.5 gravitational radii. Okay, so then you take the calculated ISCO versus spin parameter that was derived by Kerr for a spinning black hole. This is a very accurate it's an analytic calculation of how the ISCO should follow the spin parameter. Our value of 3Rg implies a spin parameter of about 0.6. So this is just one example of applying this method of constraining the spin of a quasar. We've actually applied it to several other objects that we've been observing. They don't have as many observations as RxE 1131, but we do see shifts, energy shifts in all of them. And in two additional ones, we also constrain the spin. So this potential of using this method then of measuring spins of very distant objects where other techniques are not sensitive enough to actually measure the spin. So there are different types of techniques employed for measuring spin, which are used for safer galaxies, but for distant quasars, they're very difficult to apply. So as I mentioned, we can do a consistency check just to see, are we really observing these acoustic going across? The way the Chandra observations were scheduled, because we can't really trigger we don't know when a microlensing event will occur, they have been spread out randomly during the particular cycle. And it happens in some cases, the scheduling, that two observations were planned within a few days of each other. And there were 3 cases where that happened. And this particular observation, 5 days apart, and you see that the lines are shifted by very small amounts. So we know that this particular case, we're looking at a single acoustic crossing event. And I point to where this is happening right at the peak of where the flux ratio peaks. So another confirmation that this is a microlensing event, all right? And so you can simply see by taking the known velocity, calculated velocity of the caustic, this elapsed time here, delta t, you can simply calculate the distance traveled by that caustic. And then going back to the G parameter, we can actually see by how many RGs has the caustic moved, and then convert that to get a mass of the black hole. So when we do that for the 3 cases where we have caustic crossings, single caustic crossings, by doing this simple check, we get a mass of about 2 × 10⁸, which is very close to the mass obtained from the traditional, using the broad line in the optical. And we also then, as I mentioned, just looking at the width of the microlensing event, get an estimate of the size of the corona, and we get something less than 40 Rg. So again, this is all consistent, again, that we are really observing these caustic going across an accretion disk. Another direction that we're taking is doing a more careful simulation, numerical simulations of these microlensing events. So on the left, this is done by my collaborator, Henryk Krzyzewski. He has simulated the emission of the accretion disk and also has a caustic going over that and magnifying that accretion disk. And on the right, you see the simulated X-ray spectrum. So you actually see the microlens reflection lines and the microlens continuum emission for 2 different instances, all right? So you see the iron line, but you also expect to see, as I mentioned, the other lines as well. This is something we actually are hoping to get with upcoming Chandra and XMM observations. XMM with a higher effective area will hopefully allow us to detect these softer lines, which we think are part of the soft excess, which has kind of been a mystery in AGN, people who study AGN spectra. So I want to show you one of these simulations we've done of a caustic going across a quasar's accretion disk. And you can see on the right how the spectrum changes, magnifying both the reflection and the corona. If you notice, there'll be one more caustic coming across, how both the corona, so right here, you see when when the caustic is very close to the center, it's over the corona, you actually increase the flux a lot, and that actually dilutes the reflected components. So sometimes the reflected lines are easier to pick out when you either just cross the corona or considerably before you get to it. All right, so let me talk a little bit about future prospects and synergy. So there are many planned proposed missions in the X-ray band. I want to focus on two that have sub-arc second resolution, Axis and Lynx. So these are two missions that are capable of resolving the images of lens quasars. So they're very important for continuing this type of work in the future. So not only do they have sub-arc second resolution, but they also have much larger effective area. Why is that important? Well, instead of like taking the entire spectrum and doing this analysis that I described, you can select a region in energy space. Let's say you just pick an energy region surrounding the iron line, and you do this analysis, microlensing analysis. That essentially will give you the size scale of that region of emission. Or you can pick the Compton hump, and you can say, okay, where is the Compton hump emission coming from? So you can actually select regions in your spectrum and apply this analysis because you have this larger effective area. Also,
3 minutes.
Thank you. Also, you can measure the spin to higher accuracy. And as I'll mention, you can use upcoming observatories that will significantly increase the number of known quasars. And that's where the Vera Rubin Observatory comes into play that you probably have heard about. So the current prediction is that the Rubin Observatory will discover more than 10,000 new gravitational lenses. To give you perspective, we currently know about 250 lens quasars. So this will like revolutionize the field. And the important aspect of this observatory is that it will be routinely monitoring a large fraction of the sky. So for free, astronomers will have these light curves. Having those light curves are important in the optical because then you can you can predict when a microlensing event will occur. Just like those light curves I showed before, by looking at the optical light curves, you can predict when to start to trigger your X-ray observation. That will allow one to get a high cadence of observation of a single caustic crossing event. It'll be great to have an observatory that can take advantage of that. Chandra will be able to take advantage of that, and any mission that can overlap with Rubin will be able to do that. But you might ask, well, how do we know which of those 10,000 quasars is bright enough to actually observe in the X-rays? That's where the other synergy comes about. eROSITA, which was recently launched. eROSITA will do an all-sky survey, and the data will become public in a few years. So by looking at the eROSITA all-sky survey, we can then identify which AGN are bright enough that you can actually apply this type of analysis to these new lens quasars that will be discovered. So that's what I had to say for today regarding microlensing and how we can apply microlensing to learn about some of the fundamental parameters of quasars. And I want to end by congratulating the winners of this year's 2020 Nobel Prize, which was for their research on, obviously, supermassive black holes. Thank you very much. And I'll accept any questions you have.
Thank you for an excellent talk, George. We have a question from John Miller. Especially if the field will soon have thousands of lens quasars, perhaps catching rare cases, how sensitive is microlensing to close binarity?
We have thousands of lens quasars, perhaps catching rare cases. How sensitive is microlensing? So I'm not clear about the sensitivity of microlensing to close binarity. So we will have, as I mentioned, 10,000 new lenses that will be detected. And as I mentioned, that these So maybe John can clarify what he means to close binarity.
Yeah, let's see if we can ask him to clarify.
Hi, George. That was a
Yeah.
great talk. I'm sorry that I wasn't clear. I meant that if you have two equal mass black holes that are separated by, say, the distance from a black hole to its broadline region, are you sensitive to that?
That's a very good thought and a question. We haven't really simulated that, but yeah, I would assume that you know, microlensing will be very sensitive to that. I guess the point would be, you know, how strong the signal will be, the timing, if you can predict when the microlensing event will occur. So as I mentioned, one of the key aspects is triggering. So if this is something that you can see beforehand in the optical monitoring, let's say with Rubin, and then plan a mission ahead of time. Again, I haven't really done the simulations to see how strong the signal will be, but that's an excellent thing to study and you know, to see if this would be another way of detecting binary black holes.
Great, and we have a question from Richard Mushavsky. How important is mission scheduling flexibility in following up the Rubin observatory triggers?
Yes, excellent question, because as you notice, sorry, from the optical light curves, in the optical microlensing event could last for like a year. So because the optical emission region is so large, you get to see the rise in the flux ratios very early on. So you have a lot of flexibility in time. So people are working on perfecting these trigger algorithms right now. But the idea is you do have a lot of time ahead to schedule the X-ray observation because of the fact that since the optical emitting region is so much larger than the compact X-rays, you start seeing the rise in the optical emission and the flux ratios much earlier. So I would say you have months ahead to schedule and trigger on you know, on an X-ray telescope.
If there's any more questions, please enter them into the Q&A box. I will ask a question. I don't know if you caught the Synergies panel that we had yesterday.
No, I didn't, sorry.
Yesterday there was quite a bit of discussion about releasing time-sensitive information, how to get, like, for instance, out of eROSITA. But you're mainly interested in using eROSITA to know the source flux of your candidates. You're not using it you're not thinking about using it for a time-sensitive type of trigger. That's
right. So the eROSITA is crucial just to identify which AGN are above the, you know, the threshold of being able to be detected with enough counts, so you can have you know, a spectrum where you could see these shifted lines, for example. Whereas, so I think, you know, part of it is that the Rubin observatory will be providing these, observing, you know, 2/3 of the sky, you know, a few times a week. So these light curves that, you know, have been tediously obtained by the CosmoGrail team over many years. For example, RxJ1131, it's been monitored by by many people over like the past 15 years. It's, you know, it's very difficult to do that for over such a long period. And I think the beauty of Rubin would be that those data will be available to everyone.
Mm-hmm. Great. We have another question from Elena Bertola. Maybe I missed it, but why couldn't you measure the spin of the Einstein cross?
Yes, so apparently some of the objects that we have monitored, the reflection component is not as strong. So the Einstein cross is one of them where we do not detect as many shifted lines. Plus, it's not, and part of that has to do also that it's not as X-ray bright. So this is going back to having enough bright sources. RxJ1131 is significantly brighter, so it's easier to detect the shifted lines, whereas the Einstein cross, we don't have enough shifted lines to have a energy distribution where we can have firm boundaries of, the lowest energy shift that constrains the ISCO radius. So hopefully, we're still observing more of these lenses with Chandra. Hopefully we can build that distribution and put a constraint on the Einstein cross as well.
Excellent. Thanks so much for an excellent talk. Thank you for the questions. We have one more speaker left. I'm asking them to prepare their slides. Our last speaker of this session is Sebastian Heinz, who's also an SOC member. Thank you for the input there. Coming to us from the University of Wisconsin-Madison, and will speak to us about new techniques in X-ray dust tomography.
All right, I hope you can hear me. So I thought I'd do something a little different and give a lightning talk about some new work that we've done with Lia Corrales, who already gave a fantastic introduction to dust tomography this morning, and an undergrad, Morgan Adams from FSU Tallahassee, who did an RU summer project at Wisconsin working on this. To jump right into it, here is that sketch again that Lia showed this morning of the echo from Sirsen's X1. And what you see here are these multiple rings that are created, each ring by a separate dust cloud between us and the source. And as you see, these rings actually have some structure to them. That wasn't so clear in the image that was shown before because it was smoothed to make it pretty. But what we actually measure to determine where the dust is the intensity profile as a function of distance from the central source. And so that's plotted on the top right here as a function of angle away from the source. And what you see is that the intensity has these very distinct peaks corresponding to the different rings. And each peak in particular has some substructure. And that substructure is actually caused by the shape of the light curve of the flare that caused the echo. So the intensity profile that you see on the top right here is actually the convolution of the column density along the line of sight with the light curve, with the flux as a function of time.
Sebastian, your slides have not events. Sorry.
Okay. Oh, can you see the slide?
Yes.
With the rings?
Yes, now we can.
Okay. Okay, sorry. Oops. Okay, so what you see on the top right here is the intensity profile as a function of angle away from the source. And the structure of this intensity profile is the convolution of the column density along the line of sight with the light curve. So mathematically, that's the formula that governs the intensity profile. And so if we know the light curve of the source, we can actually deconvolve the intensity profile with that light curve to back out the column density along the line of sight, that quantity here. And that's shown on the bottom plot here, where as a function of angle or as a function of distance, you see these 4 distinct dust clouds. And so this is easy in the case of a bright echo like the one from Sirsen's X1, but it is hard if you have low signal to noise data, a number of short observations, where you try to deconvolve every single observation with a light curve. That becomes very difficult. To demonstrate that, here is a synthetic set of observations, 30 distinct observations of the same echo, and as a function of angle and observation number, and you see that this echo propagates away from the source, and this echo is caused by a single flare in X-rays and 2 dust clouds, right? So this is simulated, and for a bright echo, you can see that this works remarkably well. The blue light curve, the blue curve here is the column density distribution, and the orange is the reconstructed average deconvolution for all these 30 different observations. But when we decrease the signal to noise, you see that the actual reconstruction becomes worse and worse. And at some point, you completely lose the signal. And I hope you can see this. I see it on my screen, but please let me know.
No slide. No slide. Yeah, next slide, please.
Oh, okay. So can you see the slide?
Yes.
Okay. I don't know why it's not advancing, but so what we see here are these 4 different cases of an echo, synthetic simulated echo, where the signal propagates to larger angles and the signal to noise decreases as we go down. And at the bottom panel here, you see that 30 individual deconvolutions of the echo with the light curve don't reproduce the dust column density distribution, which is in blue here. Now, to remedy that, we've developed a new 2D Lucy-Richardson constrained deconvolution algorithm that deconvolves the entire set of light curves and the entire set of echo observations all at once. And as you can see, as we decrease the signal to noise, the reconstruction is remarkably good until we reach fairly low signal to noise where you can't even see with the naked eye that there is an echo at all. We still reconstruct most of the dust, but you can, in this case, actually increase the fidelity of your measurement by increasing the number of measurements. So if we go to a larger number of shorter observations, we can actually reconstruct the dust column density distribution, which is shown on the bottom right here, and which I hope you can see. Let me just make sure that,
yes,
that you can see it. That you can see it. So on the bottom right here, you can see the improvement that you get for increasing the number of observations for low signal to noise data with this new deconvolution algorithm. And so this is shown in the KS test, where it's significantly better reconstruction of the cumulative column density towards the source. I don't know how much time I have left. Since my slides don't advance. Okay, so I was going to put up a short Synergy reminder of why this talk is in the session. Observing these echoes allows us to combine X-ray observations with observations at, let's say, CO, and also at dust in the optical, to then reconstruct the dust distribution and the distances to all of these contributions. So I will put up my summary, and I think I'll just do this way. Zoom is not collaborating today with me, but I'll put up my summary. Given a well-sampled light curve, we can reconstruct the dust column density distribution for low signal to noise data with this new 2D Lucy-Richardson deconvolution algorithm that we've developed that is constrained. We're optimizing it for the Poisson regime right now, and we'll let it loose on a number of archival observations, as well as enabling more sensitive and accurate future observations. And since this work was partly done as part of our summer program, if you're an undergraduate or are working with undergrads, consider the summer RU experience at Wisconsin. Thank you.
Thank you, Sebastian. Apologize for the technical difficulties. The slides were not advancing.
Yeah.
But we did get to see most of the slides in the end. Fortunately, we don't have any time for questions for this session, but thanks a lot for everyone, all the speakers that we've had in the session, and thank you all for joining. I think that was a really excellent session that really highlighted the synergies with different wavebands, but also within the same wavebands, and also really showed how timing is important for a lot of these studies. Please join us for the next session, which starts at 11. You'll have to go to the other webinar link that I sent you all. Thank you again for joining. Bye.